Hey AP Stat, welcome to the fourth and final part of 3.2. This chapter in this 3.2, this epic section of dealing with least squares regression equations and so on. So we're actually going to finally get to how do we actually calculate this by hand if we wanted to. We've already done it in a calculator. We kind of saw what the output looks like in a computer, but so that's often how it is done. But how do the calculator actually do that? How do they find that minimize of that squared residuals to find that line of best fit? Well, we have some formulas that if you want to kind of show why the formulas works, you're gonna have to get into some calculus with it. We're not gonna go there, but I do want to show you at least the formulas that you can work with and then help you kind of understand them at least on some level. So often technology is the best way to find it, but we can calculate it using only mean standard deviations of the two variables and their correlation. So it's a relatively simple equation that you come to when you're doing those minimized squared residuals. And again, you use kind of the calculus to figure out how this works. And so these are the formulas that show up on your AP test formula sheet. So if we have data on an explanatory variable x and response variable y for n individuals, from the data, calculate the means x bar and y bar for the standard deviation and the standard deviation of x and standard deviation of y. We already maybe did this if you've calculated correlation. If you thought about we got to calculate correlation, we needed those values to find our z-scores for the x values and the y values to find that correlation coefficient. So we need those. We also need our correlation, and so we can actually fill in these values for the least squares regression lines, the y-intercept and the slope, using these two relatively simple formulas. So the slope, B1, is you do the correlation times the standard deviation in y over the standard deviation in x. Think of slope, again, slope, you can go back to this concept of its rise over run, right? The change in y over change in x. Well, that should kind of make sense. The standard deviation y over the standard deviation x is kind of a typical distance in y over a typical distance in x. However, we multiply it by correlation, and there's a few reasons. One I'll get to in a second, but the other reason is that standard deviations are always positive. We realize that we need to also have negative slopes sometimes for and so that's actually what the correlation brings to the table. Correlation brings the sign to the table. I'll also get back to another thing with why we multiply by that correlation. And then our y-intercept, once we have this slope, B1, once we plug that in, we're going to actually plug in the point x bar, y bar. So it's the average x and the average y. It's kind of like point slope form. We want it to go through the average of the x's and the average of the y's. And that's where we kind of anchor our sloped line too, is that just right in the middle of our x's, right in the middle of our y's. And so that is a point that will always be on our least squares regression line if you have the average of your x's and the average of your y's. All right, so let's take a look at kind of a complex looking image, and I'm going to try and explain this as best I can. So what we've got here, we've got a scatter plot of some points. And so this vertical line we're seeing here is actually x bar. It's the average of the x's. And this horizontal line there is the average of our y values, the average of our heights. We're predicting height from foot length in this case. All right, so that's x bar, y bar. That point will be on the graph. And so part of that equation is doing that. All right, then the slope from there, so what they're actually showing here, this red line is one standard deviation above in y, and then this greenish line, I guess, over here is one standard deviation in x to the right. So what we do is, like, say somebody is one standard deviation above average in, like, foot length. If we went to this point, that would be one standard deviation above average in height. And so what you could think, maybe we would make that prediction that if we would go above one standard deviation of average of x, we'd go up one standard deviation of average of y. But that's not quite what we expect. We actually expect what we call regression. And so that's where this idea comes from. We expect regression toward the mean, right? And that's what this prediction equation will end up going back a little bit closer to, rather than going a full standard deviation, we're going to go this distance here. And that distance is actually, we do r standard deviation. So our slope, if we go back to this equation here, you can think of rise over run. If we could actually multiply that r up into the numerator, it would be r standard deviations of y per every one standard deviation of x. And that's that multiplier. And so if you have a really strong correlation, we actually would predict, if your correlation is 1, we would predict you would go up 1 standard deviation of y per one standard deviation of x. However, more often than not, we don't have a perfect linear relationship, so you go up r standard deviations of y per 1 standard deviation of x, and that's what we end up with here. This slope ends up being, and this here ends up being that kind of fraction of a standard deviation. And if it were negative, it would be going down, right? So we would have a negative slope. If we had a negative r, it would be down here, but it wouldn't be a full standard deviation below average. And that's kind of, what we expect. If I was going to predict your second test from your first test, if you performed a whole standard deviation above average on the first test, what we expect is a little bit of regression toward the mean. I wouldn't necessarily predict a full standard deviation above average. I would still predict above average, but not a full standard deviation. It would be, expect kind of some regression. And then same thing if you're below average. If you started the standard deviation below average, we expect some regression toward the mean, that you're going to end up being a little bit closer to the average in our prediction. And so that's how we get that that line, and that is that concept of regression. So that's kind of what this is saying. So we've got that line here. They've put those distances on there. And so for an increase in 1 standard deviation of the explanatory variable, the least squares regression line predicts an increase of r standard deviations of y in the response variable. So this is called regression of the mean because the values regress to their mean. Ultimately, that's a pretty complex concept. I haven't seen a lot tested on that, more than, in this image. I wouldn't say that you'd have to understand that. More so just understand the concept that, like, the point that it goes through is x bar, y bar, that the average of the x and the average of the y, our line will go through that. And then that rise over run is r standard deviations of y per 1 standard deviation of x. That's how we get that slope. So that's the only way I've ever seen that show up on like the AP test. I wouldn't expect you to have to interpret an image like this, because it is a complex concept. All right, last thing for the chapter. Some correlation and regression wisdom, some things to look out for, some things to be aware of. Correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, you should be aware of their limitations. I've already gotten some of these ideas, but so correlation and regression lines describe only linear relationships. All right, so if we have this, data like this, we'll get a correlation, and actually. You could kind of guess that correlation is, fairly strong. But you'll get a correlation for this equation, you get a correlation for that, go to a correlation for that. In fact, all 4 of these have the exact same correlation. Sorry about that. All 4 of these have the exact same correlation, and they actually all have the exact same least squares regression line. But they're all very different. So the only one of these that really that linear regression would be appropriate for, and that's an appropriate measure, that correlation is an appropriate measure for, is this first one, because that's actually linear. Here, it's, that 1 point's throwing it off. Otherwise, this is a perfect line here. This is like, there's no relationship, but then all of a sudden that 1 point, and then this is clearly curved. You could do better if you modeled that with a curved relationship. So be aware of kind of the weaknesses of just plugging things into a formula. And, you need to think as well when you're doing this. Correlation. We should also be aware of correlation is not, and least squares regression are both not resistant. So that can hurt us in a number of ways. So this here, we have basically no relationship between these variables, but then this one variable out here ends up bringing our least squares regression line down there and actually gives us a relatively strong correlation. So it's going to affect it a lot. If we look at the residuals for this, we've got, those residuals just look, it looks really weird. We have kind of our outlier over here where that kind of fits our trend, but our trend only, for the most part, only exists through the existence of this. If we actually took that point out and this point out, we actually maybe even see a weird curve going on in the rest of the data. I'm not sure if it's enough to call that a trend, but, and then we have those residual there. So we have two kind of outliers that are going to have a big impact on those points. And so we can actually think about how would that affect those. So if we did the prediction equation, we get this green one. If we took the child 19 out, we see it changes slightly, comes down a little bit. But if we took this point out, that regression equation changes quite a bit. And we can also look at how does those summary statistics change, and basically how the error, like for if we took out child 18, if we can think about the percent of variation explained, we see that R squared goes way down. Because that child has a big influence on all of that, if we didn't have that. And then if we take out 19, that has a big impact on S. When we take out child 19, that's standard deviation of the residuals. So they're all very much so impacted by those outliers and those influential points. So last thing, you've heard this probably for a long time, association does not imply causation. A lot of people like to say correlation does not imply causation. And that's true, although a lot of times people use the word correlation when they're talking about categorical variables and things like that. Technically, correlation is strictly linear. So statisticians, we like to say association, because that's a more general term that can come with any relationship, not just a strictly linear relationship. And so association does not imply causation. So if we study the relationship between two variables, we often hope to show that changes in the explanatory variables cause changes in the response variables. Notice that's not always implied. We can explain a response from an explanatory variable, but that doesn't imply a cause effect. A lot of times we think that it should, or it does. So strong association between two variables is not enough to draw conclusions about cause and effect. To get to cause and effect, we've got to, and this will be a big topic of next chapter, we've got to do a properly designed experiment. It could be a number of potential relationships that are going on that we're not thinking about. So just because two variables are correlated doesn't mean that it's a cause-effect relationship. And people do this all the time. They say, oh, well, this people with this, they're more likely to that. And they're implying a cause-effect relationship just because they've noticed these trends. So be aware that that's out there when you're using your correlation and regression. And we'll get back to that even more so when we get into our experimental design and stuff from next unit.